Alright, so it's been a fairly long day, but I got a load of study done, a load of work done, and I'm feeling really, really pleased with myself. So I thought I'd give myself a bit of a break and do a quick programming challenge just to see how I got on. So I've jumped onto Daily Programmer, which is a great website for just finding little projects to do. And I found this one which seems kind of interesting. Basically what you have to do is read in guitar tablature as your input, and you have to output what notes are represented by the tablature. So the way tab is read is each one of these lines represents a string on the guitar. The letter here represents the tuning of that string, so this string is tuned to E, this string is tuned to D. There. And then the number represents where you put your finger. So this here would be your second, or your finger on the second fret of the A string, which raises that note to a B. So the program would output a B in that case. So it's a really, really cool, simple little idea. I'm not 100% sure exactly how I want to solve it, but sure, I said I'd give it a go and see how it turned out. I'm going to code it in C just because I want to. I've already downloaded some of the sample input files, and yeah, I don't know, let's see how we get on. So I'm going to start by just setting up the boilerplate kind of code, so stuff for reading in the file and making sure that there is a file there in the first place, that kind of stuff. So let's see how we get on. So, yep, that's grand. That seems to work okay. So one of the things which I kind of noticed, what I'm actually going to do is I'm going to pop open one of the sample files so we can have a look at it. All right, so we essentially have, 6 lines of input, right? Let's just assume for now that all the tablature is going to be on one line. Let's assume that the guitar will be in standard tuning, E, A, D, G, B, E. So we're going to skip those first 2 characters on every line. And every time we encounter a new line, we're going to move on to the next string. So what I think I'm going to do is set up one sort of longish array that is the same length as a single line of the file. And just through multiple passes over each line, I'm gradually going to add notes to that line in a numerically encoded format, right? So taking A, let's say that A is 0, for example, right? Then this would go in as 2 and this would go in as 0. That's fair enough. But E would be A, B, C, D, E would be 5 plus 3. So this G note here would go in as 8. So one array, which I'm just going to build up as a big, long list of encodings. And each time we hit a new line character, we'll rewind to the start, move that through that array again, and sort of populate it. So it's messy, and there'll be a lot of redundant space in the array, but I don't feel too bad about that. Like, we're going for a fairly simple, straightforward, quick solution. It's late at night. I think maybe the next thing to do is, all right, let's set up our guitar strings, and let's set up a function which will convert which will convert one of those numbers to, actually, no. Maybe the next thing to do is to just set up a little loop to read each character from the file. That actually might make a bit more sense. So we'll start by actually loading in the data, and then we'll kind of figure out what to do with it. Okay, yeah, let's do that. All right. Yeah, that's fair enough. So we'll store the tuning like this, right? So that's E, B, G, D, A, E. And ideally, we'll have some function that'll do a conversion from notes to numbers and numbers to notes, and that'll just make everything a bit more legible. But for now, let's just leave that as is. That's fine. Okay. Yeah. So you sort of have to bear in mind that there are sharp and flat notes in there as well. So I was a little bit wrong earlier when I said that E was I think I said it was the fifth note. It's actually the seventh note because you have an A sharp and a C sharp and a D sharp in there as well. And then the other thing, the thing that sort of makes musical notation in general kind of a pain to deal with, is that the interval between E and F and B and C are both semitones, but the interval between every other natural note is a full tone, so two semitones, and then a semitone is usually the note sharpened. So A plus a semitone is A sharp, but B plus a semitone is C, not B sharp. So we're going to sort of have to work around that. Okay, but so we now know kind of the root tuning for a string. I think the next thing for us to do is to set up. Okay, to begin with, I'm just going to have a fixed length array storing notes, and then later we might kind of use malloc and realloc so that it expands depending on the length of the input. For now, I'm just going to hard code it to 2048 characters. That should be fine. Yeah, I think that'll be okay. Okay, yeah, let's do it this way. So. Okay, so yeah, that's loading our notes into our array. It's not the tidiest it could be, but that's okay. So the next thing that we want to do is we want to modify the note with the offset of the string. So what we basically said before, each of these codes is like an offset that needs to be added to the value of the note to get the actual note tuning, whatever the actual interval. So what we're going to do is note plus the tuning of the guitar and the string that we're currently on. And hopefully I've got like a little scrolled set of codes for each note here on a piece of paper. So if I make this and test it, it should roughly line up. We'll do it the messy way for now, and I'll come back and make it better later. Like that note is probably going to end up having to be a string anyway, because right now we're not accounting for any note over the 9th fret. So because like the 12th fret is going to be 2 characters, we're going to need to do some sort of a look ahead. But we'll worry about that later. Like my goal for now is to just get the simplest possible thing working and then sort of gradually work on our way back to something more complex. right, so that's reading the notes. It's storing them in the stave, and then basically what I did was in the stave I sort of initialized the whole thing to be -1, which is the only reason why stave's an array of type char. It's because memset works in bytes. It was easier to do that initialization to -1 if I used a character array. There's no other reason to do it than that, really. So I guess the next thing to do is to write a function which converts those numbers to their string equivalents and then prints the string. So I guess, see, I'm always really wary of using strings in C because they're strange sometimes. What I think I'm going to do is I'm going to write a function which has a static variable declared in it, which contains those notes. And I think the fact that it's statically declared should mean that I'll be able to return a pointer to it, I think, without there being any real issue. And that way, so the function will return a character pointer, you'll print the string, and I think everything will be okay. I think. We'll find out. If it does work, then this now, because of the way we've done it, is just a string indexing problem, right? Or an array indexing problem, rather. So the note to which a number evaluates is just the integer mod 12. So we're basically saying that 12 is also A. So 0 encodes to A, 1 encodes to A sharp, and then because we've taken the tuning of each string into account, we've already translated those integers to our sort of normalized notation scheme. We basically have all the notes on a single infinitely long string that's tuned to A, and we're just figuring out what to print then for each integer value on that string. So I'm just going to write a function to do that, and let's see how this works. Okay, so that seems to work. So just let me see if I can pull up, let me just do like a full screen grab here so I can show you what we've got. Give me 2 seconds. And we're back with a horrible recursive screen. Sorry about that. Right, so here's the code. And here are some of the sample outputs that I was using, right? So we have this guitar tablature notation, and when I feed that into my program, what I get is, so I loaded that as sample 1. There we go. So we get the expected output B, A, G, A, B, 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 A, 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 B, D, D. If I load the second one, sample 2, then I get the expected output. There was a little problem there where I had encoded G to be 9. It should actually have been 10. So those Ds were coming out as C sharps. But that's fine. So we've sort of solved for the simplest base case. Obviously there's a little bug there at the end where that 12 should be a B, but it's getting encoded to, or sorry, that 12 should be a D, but it's being encoded to a D sharp and an E, because we're not accounting for strings that are, for numbers that are greater than 9. So we should kind of go back and fix that. And that's where the A to I function is going to become kind of useful. So I need to think for a second about exactly how I want to do that. Because you're sort of like, you're always kind of looking one ahead. And I don't want to have too many like if statements sitting in there where it's like, if the array is empty, don't do something kind of stuff. So this seems like the kind of thing that should be simple enough if I just think about it for 2 minutes and then get back to it. But once we have that solved, it would be kind of nice then to have a note to num function, which we could use to initialize our tunings up the top here, and then we can start thinking about octaves. So actual octaves above root C and stuff like that. That'd be another step to consider. So what would happen in that case is the number would map to a note, but the remainder of that number would be indicative of, or what is it? Not the remainder. The number, yeah. The number of times that num notes divided into the particular number encoding will be the octave to which that note belongs, right? So like it's really simple arithmetic. I'm actually just, again, more so concerned about the actual string processing thing. So I'm going to take about 2 minutes to think about it and then sort of knuckle back down to this thing and try and solve for that, numbers which are greater than 2 digits. I want to solve that first and then I'll worry about octaves. Okay, so I've had to think about how we're going to do this, and I guess the only real way that you can do it is to populate an array, which is fine. There's nothing wrong with it. It's just it sort of means that there's going to have to be an extra sort of if statement in there. So what we'll do is if we encounter a digit, we'll add it to the array, and if we encounter something that's not a digit, we'll check to see if the length of the string in the array is greater than 0, and if it is, then we'll call a to I, which is ASCII to integer, and we'll get its numerical encoding and store that back in stave. Otherwise, if it's not empty, we just keep processing. The only reason why I don't like it is because of the extra if statement to check for string length, and there's nothing wrong with that. It's just sort of a personal tick. It feels like there should be a more elegant way to do it. The other thing, there was one other thing. The array, it's not going to need to be any bigger than 3 characters long. Like, you're not going to have a guitar with more than 99 frets. You're probably not going to have a guitar with more than 24 frets, maybe 26 at the outside. So 3 characters, that's 2 digits and a null character to terminate the string. I think that should be fine. I think we'll be okay if we run with that. So yeah, let's go with it and see what happens. Cool, that's done the trick. Bit of fiddling around to get it right, but it's there, it's there. All right, so I guess that covers the basic requirements of the problem, I think, right? So the basic requirements were just to be able to take in a stave like this and output the notes like this. That's fine. But then there was a bonus problem which actually accounts for octaves. And I figure we may as well give this one a go as well. I mean, I don't think it'll be too difficult. I had said that we would do a thing to convert the... what was it? That we would do a thing to convert a note to... its integer encoding, right? So that we could populate the tuning array up here. But I kind of want to do this in parallel with the octave problem, because any function which converts from strings to integers is going to need to account for octaves. So let's just do that. Yeah, in fact, the easiest way to get started on this is probably just to write the note to integer encoding, right? And that's actually going to work much the same way, I think, as Yeah, much the same way as num to note above there, right? You'll pass in a string, and you'll pass in an octave encoding, and we'll just do a linear search through a static array like this. The index at which we find the string is the note number, and then we add 12 times the octave to that number to get the final integer encoding. And if we just do it that way, right? If we just do it that way, then our original program should actually still work, because, you know, modulus arithmetic won't be affected by that. It won't be until we add one extra function, which will not be num to note, it'll be num to octave. And what we'll do is we'll actually leave this the exact same, and we'll do a call for num to note, and that will return the note, and then we'll have an extra parameter there, mod I, and we'll call a second function, num to octave, and that'll return the octave number. And that should be fine, that should be a complete solution. But let's start simple here. Let's just try and implement the note to num function. We'll do that up here now. Cool. Yeah, that seems to have just worked like straight out of the bag, which I'm delighted with. So we can now go from a note and an octave to an integer encoding, and we could go from an integer encoding back to a note, but not an octave. And we're going to do the octave separately, because the octave is really easy, actually. I guess, I mean, one way to do it would be, instead of having this thing return a character pointer, you could have it take a character array and an integer pointer as arguments, and you could sort of populate both in one function. And there'd be nothing wrong with that, but I'm just, you know, we've started this way, let's finish this way. So let's just get this thing to return the integer code for the octave. Okay, so this has worked out fairly well, but there's a minor issue, which I'm going to try and pull up on screen here, which is the C3. That's C3, and I think that A4 as well are incorrect. And the reason for that, I think, is actually very, very simple. My codes start with A at 0, but conventionally music treats C as its 0 point. So I think all we actually have to do to fix this output is change what we consider to be C, the 0 point of our array, and that's, or the 0 point of our integer encoding, and that's easy to do. It's kind of frustrating. I'm just realizing now we're going to have to change it in 2 places, so there's probably a much better way to declare that array. We won't worry about it for now. Yeah, I'm just going to do a quick search and make sure that I am right, that C should be the 0 point, and then we'll flip that array around and everything should work fine, because every other output here is correct. So I think we're most of the way to a correct solution here. Yeah, that's fixed it. Cool. So I can pop the output up on the screen there if you want to see it. So you can see now that where's my mouse gone? So where it was a C3, it should have been a C4. So we fixed that. Sorry, there it is. And where it should have been A3, we were getting A4. So that was just because of where we started counting from. That's a very, very easy thing to fix. One little stretch goal and will we go for it? Will we bother going for it? Is that this obviously has a maximum bound of 2048 characters. It's fairly easy to make that bigger just by using malloc and realloc. Let's see, I've been at this for about 45 minutes now, I think. 45, 50 minutes. Will we do it? Yeah, let's give it a try. So what we're going to do is, essentially we're implementing a dynamic array here, right? So where previously we had stave, right, as an array, we're going to instead initialize it as a pointer, right? And at the start of our program, we are going to let stave be equal to malloc size of stave times, and what did I call it? Len stave. Let's call it default len stave, right? So that's our starting sort of size, and it will gradually grow from there. So stave is equal to times default len stave. That's grand. And we just got to remember to free that down here at the bottom. So we'll free the stave. All right. And what we'll then have is we will keep track of stave length here. Yep. All right. And stave len will initially be, actually we'll initialize stave len there, and stave len will initially be default len stave, and we'll initialize it like that. And we'll have an expansion rate. We'll let it double in size every time. And what we will do then is if I is equal to, well, we'll say greater than or equal to, just for the sake of it, stave len, then we will reallocate stave len. So stave is equal to realloc stave. What is our notation for that again? Okay. So what I'm going to do is, well, let's just run it initially to make sure that everything's okay there. And it's not because of memset up here. That should be stave len now. And again, so I've used len stave somewhere else. Yeah. Cool. We get a segmentation fault there. Why do I get that? Because stave is already a pointer, so we don't need to pass the address. There we go. Okay. So, yeah, that's working. So now let's set our array size to be something absurdly small. We'll just let it gradually grow. So we'll actually just start it at 1. And essentially what we should see is it should still work without any problems. It should grow to meet the size of the input. No, that actually gives us a problem, because every time we extend the array, we have to initialize, we have to do a memset from the middle of the array out. Yeah, we have to, I can see the problem. So just to show you the output that I'm dealing with here, So these C0s are because after the realloc happens, although, do you know what? No, it's because the starting point is so absurdly small. It's because it starts at 1. Yeah, so this is actually probably simpler than I think, right? The solution is going to be in here just after the realloc, and what we want to do is we want to do a memset from the old stave len up to the end of the new stave len. Alright, so I had to think about that one for a little bit, to be honest. This is why dynamic memory can be such a bloody pain. So yeah, basically just reallocate the stave to the stave length times some growth rate, right? So we let it double in size every time, which is pretty quick, but that's fine. I'm not too worried about it. We then have to re-zero all of that newly allocated memory, right? Because we're using -1 to indicate that there is no note there, right? That a note should not be played. So we have to set all of our newly allocated memory to -1 without writing over all of our previously allocated memory, and then we just update our stave length so we can keep an eye on it. I'm not sure if I have Valgrind installed on the computer here, but let's do a couple little checks just to make sure that this program is working as expected and everything's okay. Okay, so let's first of all show that everything is definitely doing what it should do. So here's our sample input 1, right? It looks like that, and if we run our program across that sample input data, we get our expected output. So those are the notes that are being played. If we do that again for sample 2, again, these are the correct notes. I've checked these. I'm fairly happy that everything works okay. And then finally for sample 3, there we go. Now, because we've done some dynamic memory allocation, I'm also going to check for memory leaks using Valgrind. So we'll just use Valgrind -- leak check full, and we'll run it across the second data set. Oh, it shouldn't be that // excuse me. There we go. And you can see there it says all heap blocks were freed, no leaks are possible. So 11 allocations, 11 frees. That looks good. So it seems like we've built a fairly decent solution to that little test problem. I'll throw my source code up on GitHub with a few comments. So if you want to download it, have a look at it and play with it yourself, you're more than welcome to. And feel free to leave any comments or advice, or if you have any insight or better solutions of your own, just let me know. All right, take care, folks.